Hey, beautiful class. All right, we're gonna do this practice exam for exam 2. That's over chapter 14.1. That looks like some weird, that is 1 to 15.6. And let's get into it. We got a little bit to cover, and I just want to make sure we get this as soon as possible. So it says, what is the rate of reaction with respect to NOCl for this thing? If you remember, rate for the reaction equals, and it depends on which thing. So in fact, let's do these other two and then we'll get to the answer there. So if it's on the reactant side, we're going to be losing things, so our rate's going to be negative, so we want to make sure that we have a negative there to cancel it out. 1/2 times the change in NO over the change in time. So that would be with respect to NO. That also is going to equal the rate of the CL. So it would be, there's no coefficient in front of the CL, so it's just a 1. It'd be change of the CL2 over change in time, and that would also be negative, which is also equal, so we're losing these and we're gaining this one to the positive of this one. And again, the rate has to be 1/2 because we're making twice as many of these. And this is going to be change in NOCl over change in time. So the rate with respect to NOCl we are looking for is that. All right, question number 2 says write a balanced reaction. So kind of using similar information, let's go the opposite way. Can we write a reaction? These are not in any particular order, but I can look pretty quickly and say that's negative. That means this must be on the reactant side. And these guys are positive, meaning they must be on the product side. So I'm going to start with these negative, the -1, and it tells me that it's N2O, and that half there tells me that it's going to be a 2. So that's going to be my reactant. I don't see any other negatives. That means the other two must be positive. Here I see that this is 1/2, so that means I must be putting a 2 in front of the N2. And then I got an O2 with no coefficient. So that looks like that would be my balanced reaction for these relationships. All right, moving on, number 3. It says, what are the units of K in the following rate law? Units seem to really throw people off, so let's do this a little slower. What you have to understand, in case nobody's ever gone over this, or maybe you've missed it a few times, just throwing some relationships out there before we get to actually solving this problem. All right, if I have like an M times an M, that equals that. Or if I have an M times a 1 over S, that equals M over S. If I have an M times an 8.5 divided by an M, just a 1M, this 8.5 is going to cancel out. We're going to lose 1 because it's going to be divided by this. And that's going to become M to the 7.5. So if we take an 8.5 and we divide it by something, we're going to get a 7.5. And the same thing if you multiply something instead of subtracting, because that's all we did. We took 8.5 minus 1 gave us a 7.5. That's what happens when you divide. You subtract exponents, and when you multiply, so if I have like an M times a 3.5 times an M to a 2 or a 2.5, let's go crazy here. When you multiply, you add. So 3.5 plus 2.5 is equal to 6. So that'd be an M to the 6. All right, with that information there, let's move on to this. So this is, what are the units of K in the following rate law? Well, rate is always going to be M over S. By definition, that's what rate is. We're going to set that equal to K, which we are solving for. What are those units in that K? Times concentration to the 2.5. Well, we know that concentration units, these brackets mean M, and this must mean an M to the 2.5. We're going to get K alone, and we're going to see what we're left with. So the first step I'll do, let's make sure we take our time on this one, is to multiply that times that. Remember, when you multiply exponents, you add them. This doesn't have it written, but it's a 1. So an M times an M to the 2.5 is equal to M to the 1 plus 2.5, which would be 3.5. All right, again, we want to get K alone, so you can divide each side by M to the 3.5. And what that does, that cancels, is now we have a big M over m to the 3.5 s. And that equals k. But it's still not simplified enough. Remember when we divide, we subtract. There are a couple ways you could do this. You could leave this on the bottom and say this is going to become a 2.5, or let's follow what we did over here. When we went from 8.5 to a 7.5, all we did was, this was 8.5 minus 1. That's how we got our 7.5. The numerator minus the denominator. So in this case, we have m to the 1 minus the 3.5 all over s. 1 minus 3.5 is negative 2.5. In other words, this is m to the negative 2.5 over s. And remember, this is any s, anything that's on the denominator, you can bring it up to the top by just putting a negative sign in front of it. And this would be our answer for the units of this thing. So if that didn't make sense, go through, do it a few times. The most important thing is you recognize when you divide exponents, you subtract them. And when you multiply exponents, you add them up. And that should hopefully really help. Okay. Number 4, determine the rate law and the value of k for the following reaction using the data provided. All right. Okay, so I realized, I'm gonna get another piece of paper. This can be a relatively difficult concept, especially when we throw solving stuff with log that we haven't seen in forever. I'm gonna get a new piece of paper here. All right, and especially when you can't see things very easily when you're looking at the reaction. So remember, if the reactants doubled, one of the reactants doubled and the initial rate doubled, then it's going to be a order of 1. If it tripled and the rate tripled, it's going to be an order of 1 as well. But if it doubled and the other rate quadrupled, it'll be an order of 2. But that is all great and dandy, but here's what it really says. We're looking at the change. Essentially, we're saying, hey, what was the change in concentration? And that's going to be raised to a certain power in order to give us the change in rate. Okay, bear with me. I'm going to use what we already know to do this. I'm not going to do this first one here. I'm going to move on to this I minus here, just because that's a little bit simpler. Okay, so as we went, we're always going to look for where one of them changes and the other one stays the same, right? So I see that I minus changed between there and there, right? Between that and that, it doubled. In other words, our change in concentration was a 2, but this guy stayed the same, so that's good. And then we look at the rate. 3.33 to 6.65 is a change in 2 as well. So this was our change in concentration to some order that we're looking for is equal to the change in the rate, which also happens to be 2. It doubled. So this one doubled, that one doubled. Therefore, 2 to the what equals 2? 2 to the 1 equals 2. The order of I minus must be 1. So when we go to write the rate, we'll just remember this order equals 1, the full rate law. All right, and then we move on to this one. Okay, so we're always going to be using this idea. In fact, this is the idea we've been looking at the whole time. I don't think I've ever written it this way, and I think this might have really helped if I did. So I'm sorry if I haven't. But we're looking for where this one changed and this one did not. That looks to me between the first one and the second one. So here I went from 3 to 4.4 or 0.44, and the rate changed from a 4.54 to a 6.65. All right, so if you're like, what do I do? Have no fear. Let's do this. Okay, so the difference between here and here, you would find by dividing it. Let me find a calculator. Okay. So the difference between these two, you would find by dividing it. So you got a 0.44 divided by a 0.3. Okay, that gives me 1.47, or about 1.5. It's okay to round a little bit on these. In other words, my change in concentration was a 1.5. I know I'm going to raise it to some value that I'm trying to solve for this one, and it's got to be equal to the change over here that I saw. Okay, the change over here I saw when I went from a 3 to a 4, this went from a 4.5 to a 6.6. So how do I find the difference there? Take the bigger number divided by the smaller number. 6.65 divided by 4.54, and that gives me a 1.5. So what must your x be? Has to be a 1. Now, if you did not know that, in fact, let's set this up. We did it in the lecture notes, but nevertheless, I think it's important to go over it again. If you have something like, let's say you had 8.7 to the x equals 43.2. I don't know what it is. Now you can go through your calculator and guess a whole bunch of numbers, which is kind of fun, especially if it's a really round, easy number. Or you could take the log of both sides. When you take the log of both sides, here's what happens. If I take a log of 8.7 to the x, what happens is that x comes out here, and we got x times the log of 8.7 equals the log of 43.2. And now we can solve. We say x is equal to the log of 43.2 divided by the log of 8.7. And that's how you solve. I just divided each side by log of 8.7, by the way, to give you an idea of how I got that. So that cancels, and now we have x equals that over that. To solve for that, we would say log 43.2 divided by the log of 8.7. And we get an answer of 1.74. That means 8.7 raised to the power of 1.74 will give us 43.2. Let's check it. 8.7 to the power of 1.74 equals 43.2. We rounded a couple times in there, but you get the same answer back. And that is how you solve for x. So even if you have a crazy couple numbers up here, you can still do this to solve for it. But I think the most important thing is to recognize this, that the change in concentration to the x is equal to the change in the rate. All right. So let's move on. Next question says, how many half-lives are required for the concentration of a reactant, some reactant, to decrease to 12.5% of its original value? All right, so if something starts off at 100% of its original value, which it ought to, after one half-life, which we denote with T in the little 1/2, it's going to be down to 50%, kind of like we talked about with caffeine, and higher body loses half of its caffeine every 5 hours. All right, so with one half-life, it's down to 50%. Another half-life later, it's lost half of that 50%. In other words, it's 25%. And then another half-life later, it's lost another half. In other words, it's 12.5%. And the answer to this question is 3 half-lives. 1, 2, 3. You had to decrease it by half 3 times in order to get 12.5%. All right. Okay, this next question I'm kind of regretting writing, just because I could have made it easier, but I'd rather give you guys the hard stuff now and make it surprisingly easy on the exam comparatively. So let's do this. All right. They gave us 3 elementary steps. Remember, elementary steps are just guesses as to what could have happened to create an overall reaction. And we'll learn about reaction. We can learn about the reaction intermediates, and we can use them to solve the rate law as long as we know which one is the slow step. So let's do all of these things. First, question A says, what is the reaction? So the overall reaction for this thing, we have to add these things up. In fact, I'm going to rewrite them here just to make it a little clearer and so I don't screw everything up and have to undo it. So we got Br2 plus some m equals an equilibrium with Br plus Br plus m. The beautiful thing is this looks like it's not actually getting used up in the reaction and we can get rid of it. Then we have, it's on both sides so we can get rid of it. Br plus H2 going with HBr plus H. And in the third step, we have H plus Br2 yielding HBr plus Br. All right, so let's add these reactions up to get the overall reaction. All of the elementary steps must add up to get an overall reaction. Okay, so anytime you see something that can cancel, you should cancel it. So over here, for example, I see a Br here, I see a Br here, either one of them could cancel. I see an H here and an H here on either side of the reaction. So if you see something over here on this side of the reaction that equals something over here on that side of the reaction, they are going to cancel. I'm looking to see if I see anything else. I don't. I got a Br2, a Br2, an H2. And over here I got a Br, HBr, HBr, and a Br. All right, so as far as I can tell right now, my equation is Br is a 2Br2, because I got two of them, plus H2, yielding, and then over here, it looks like I got two HBRs, plus two BRs. BR is not a common thing that you run across. All right, I like to make sure that it's balanced, just to see if it makes sense. So over here I got 2 times Br2, which would give me 4, plus 2 hydrogens. So I got 4 BRs and 2 hydrogens. Over here I also have 1, 2, 3, 4 BRs, and I have 2 hydrogens. So that's good news. It's balanced. That helps. So this is our answer to A. That is the overall reaction. We added up each of the elementary steps and we got the overall reaction. And part B, it says, what are the reaction intermediates? That's the stuff you crossed out. In class, I said, well, if it's in the original reaction, it's kind of hard. You got to be careful about saying it's a reaction intermediate. And that's true. But at this point, I don't care. If you crossed it out, just write it. We have an M. That was a reaction intermediate. We have a Br. We have an H. Anything else? No. And what I meant by that is we have a Br here and we also have a Br here, and I think it's necessary to clarify that Br is a reaction intermediate, but it is also a product. So these are our reaction intermediates. Intermediates. Okay, last but not least, this is my favorite. What is the rate law for the rate law expression for the reaction? Okay. I just realized I didn't even finish this question up here, by the way. If you're pissed about that, sorry. We found the rate order of each of these to be 1, but the rate law for this whole thing would be rate equals K times S2 O8, the 2 negative raised to the power of 1 times I minus also raised to the power of 1. So 1 and 1, and that would have been the overall rate law. The overall rate order for this reaction would have been 1 plus 1, which is 2. All right, now that I answered the question 2 questions ago, let's go back to this. What is the rate law for the expression? So to find the rate law, you have to look at the slow step in the reaction. That's this one right here. It was Br plus H2. The beautiful thing about this is we're not looking to solve for these. In the elementary steps, we already know that this is where the rate was born. This is the slow step is always the one that determines the overall rate of the reaction. So this is going to be rate equals K times BR times H2. It's that simple. So this is going to be our rate law. The problem is, in our overall reaction that we came up with here, do you see BR as one of the reactants? I don't see BR as one of the reactants. And because we don't see BR as one of the reactants, that's where we have to go through and solve at another location for BR and replace it with something that we know, preferably BR or preferably H2, or actually that's pretty much our only option, or something else that you actually see in this reaction. Okay, so in order to do that, we are going to do some replacing. All right. Well, let me get a piece of paper. All right. Okay, so right now, just to remind you, we have rate equals K BR times H2, where we have H2 in the original reaction that we came up with right here. What we don't have is BR. So let's go ahead and find something else that has BR that maybe we can replace something with. And I look immediately up here to reaction 1 because I see it's got BR. Whoops, I got excited and knocked things over, so there we go. Okay, where was I? Okay, so I look at this reaction 1 and I see that it's got BR 2, but it has BR over here. And that actually works really well because it says it's in equilibrium. So generally when we're going to replace things, they provide you an equilibrium reaction to look at. That's kind of generally the one you're going to know what to do with. All right, so we want to replace this BR. All right, in order to do that, let's take a gander at this first equation. This is BR2. I'm going to ignore the M because they're going to cancel out on both sides. Is in equilibrium with a BR plus a BR, which we would just normally write 2BR. Okay, so when we go to write this equilibrium expression, we're going to say, if we were to write a regular one, we'd say rate equals K times BR2. But that's only the rate of this one going forward. There's also a reverse. And the rate of the reverse reaction equals K times BR squared. And since we know that rate forward must equal the rate going reverse, so that whatever rate's going this way has to be the opposite, equal and opposite in the other direction. It has to be the exact same rate, that these two can be set equal to each other. In other words, rate forward equals rate reverse. My K BR2 equals K BR squared. Cool. All right, now remember, we're trying to replace this BR right here, meaning we want to get BR all alone. So let's do that. And I should forward, reverse, forward, reverse. Should make sure that we label these K's to keep track of them. Okay, so we want to get BR all alone. In order to get BR alone, we're going to divide by the K reverse on both sides. And then, we have to take the square root of it to get rid of that square. Now we have BR alone. Now we can take this and replace that sucker in there. Okay, so now our rate equals K. I'm going to replace this BR with this whole thing right here. So it's K times the square root of K forward over K reverse of Br2, which is something hopefully we recognize a little more, and then times this H2. Once we have all the K's together, we're pretty happy with that. So we can just circle those and call them K. Okay, and our rate is going to equal some K times the square root of Br2, which we would write as a 1/2, that's the same as the square root, times H2. To remind you of what we were trying to do, we needed to get back this reaction in some way, shape, or form. In other words, we needed to find out, we needed to get a reaction where Br and H2 were in it. We looked at the slow rate and said, this is our rate law, technically. This is what it should be, except Br isn't in this original reaction. So we had to find a way to replace it. Now, if this was exactly what was original, we should have been really happy. And we would have taken it. And I foresee myself asking more questions like that on the exam. But something like this might be a fun bonus question. Okay, so we needed to find Br. We went to this equilibrium expression. We set the rate forward equal to the rate reversed, and we solved for something that made sense. So we took this Br, got it alone on one side, and suddenly we were looking at just Br2 as the reactant. And we were able to put it into here and combine your K's, and then you have Br2 to the 1/2. And that's how we ended up getting the actual rate law for this reaction. And I didn't have anything to compare it to. I don't know the actual rate law, but hopefully you enjoyed that. So what is the overall reaction? Just to clarify, that was 2 Br2 plus H2, yielding 2 HBr plus 2Br. What were the intermediates? We had M, Br, which is also a product, and H. Then it said, what is the rate law for the expression? Now we can write the rate law and be confident in it. It's no longer just made up stuff that might be ended up as a product. We're actually looking at the reactants, and it's K Br2 to the 1/2 times H2. All right, hopefully you enjoyed that as much as me. I know you didn't. I'm sorry. All right, last but not least. Sweet, almost done. Okay, reaction occurred at 357 K according to the below equation, I guess I'm supposed to write. Initially, CO equals this, H2 equals that, and at equilibrium it was this. I see the word initially, I immediately think ice tables. It gave the reaction here, so with some space, so it's pretty easy to just write ice. Remember, I stands for initial, C is change, E for equilibrium. So our initial concentrations of CO was 0.27. Our initial H2 was 0.49. It did not tell us our initial CH3O as far as OH, as far as I can tell. So for methanol, I'm just going to put 0.00. Anytime it doesn't tell you what it is, it was 0. All right. Then it says at equilibrium, the methanol was 0.11. So I like to draw a line above the equilibrium. At equilibrium, this is 0.11. That reminds me that in order to get equilibrium, I'm adding I plus C, and it's going to total my equilibrium. All right, so if I ended up with 0.11 here, that means I had to have added 0.11. If I added 0.11 on this product side, in order to make 0.11 moles of this methanol, I had to have lost 2 times that amount of hydrogen. In other words, minus 0.11 times 2, or 0.22. I had to have lost this much. in order to have gained one of these, I would have had to have lost 2 of these, and that's because of the coefficient. All right, in order to gain one of these, how many of these did I have to lose? Just 1. In other words, so if I gained 0.11, I had to have lost 0.11 over here, the same amount. Now I can kind of add these things up. Here I have 0.38. That's not right. Should be 0.28. I'm doing math in my head right now, not looking at my notes. So 0.28, 0.49 minus 0.22, just make sure I'm not going crazy. 0.27, I am going crazy. And this gives me 0.16. I now no longer trust anything. Again, all I did was just take 0.49 minus 0.22 and 0.27 minus 0.16, and that gave us our equilibrium numbers. All right, now we're gonna plug this into our K. K, I ask you guys to kind of do this first because it's easy to screw up, and I should have done it, and I'm sorry I didn't. Kind of in a hurry here, but CH3OH, we always do products over our reactants. We have CO, and we have H2 squared. That's going to be our equilibrium expression. Now we just plug these equilibrium numbers in there. Move it over here. Our CH3O was 0.11 over our CO, which is 0.16, times 0.27. The only thing is we want to make sure that we recognize that 0.27 is squared. All right, so let's do this. We have 0.11 divided by 0.16 divided by 0.27 squared, and I get 9.43. Do it again. 0.11, the way I normally do it is actually 0.16 divided by 0.27 divided by 0.27. Should give me the same number, 9.43. Great. Okay, so that is our answer. As some of you in class were saying, it's greater than 1. 9 is greater than 1. Therefore, products are favored. Also known as the forward reaction. In other words, the reaction going this way is favored. Here's your topic list. Goes through each individual thing on each question. In other words, question number 1 is going to be about reaction rates with respect to individual components in a reaction. Much like the first one we did in this thing here. Question number 2, the same, and then on and on. I didn't go through everything. I'm not going to go through everything. We'd be doing 25 different questions, and then you know the answers to your test. But this just gives you a general idea, and I tried to cover multiple things in each of these that I might ask for on a test. All right, guys, have a great day. Bye.